This base upgrade introduces the threads ability, which you might have seen popping up with increasing frequency as a required ability in various core unison libraries. Threads is the new API for safer structured concurrency and resource management. In this video, we're going to cover what problems the threads ability solves and introduce its core operations in comparison to the io.concurrent API. Threads is an ability which brings structured concurrency to I/O with a modular resource safety API based on scopes and finalizers. The scope function delimits a boundary for concurrent work. It introduces a lexical block in a program that describes the lifetime of the threads it contains. Scopes can contain calls to other functions in the threads API, like threads.fork or threads.race, and can also be nested inside other scopes. Finalizers are run at the end of the scope that they're called in. The argument to a finalizer is a callback that receives an outcome value, indicating whether the scope completed successfully, was canceled, or failed. But why is this all necessary? Before, we had simple functions like io.concurrent.fork, which let us spawn a process to another thread for concurrency. And we also have promises, which are placeholders for eventual values. The promise API features a few basic operations. Promise.new, which creates an empty promise. Promise.read, which will block on an empty promise until it's filled. And promise.write, which fills the promise with a value exactly one time, prohibiting any further writes. Together, io.concurrent.fork provides a way to describe concurrent execution, and promises provide a mechanism to communicate values across threads. They're the building blocks for asynchronous programs, but they are very low level, and consequently they have many footguns. We can see some of the challenges of unstructured concurrency by combining the two. Let's take a look at what occurs in the case that an error happens on a forked thread in regular I/O. Running this code will result in a program that hangs forever. This is because the exception thrown in the forked thread is not observed by the parent thread. The set of permitted abilities in a forked I/O thread is purposefully limited to just I/O. But that doesn't stop you from spawning some work and then ignoring the result if it contains a failure. Running this program reveals a pitfall. The error in the child thread is not communicated to the parent thread. In this example, the threads ability provides a threads.fork function, which has a much nicer interface for handling errors. It can return any value instead of just unit. This program creates a scope and registers a finalizer for it that will run if a failure is detected within it. We're using threads.fork here instead of concurrent.fork. In this program, the promise is never written to because of the exception, but the program will surface the error instead of hanging. Careful readers of the finalizer function might have noticed this new cancellation option in the set of outcomes from a forked thread. That's because threads introduces the notion of safer thread interruption. Let's see what happens in unstructured concurrency without cancellation with a simple race example. This program runs two computations in parallel. One of these threads is going to be the clear winner, and since promises are write-once containers, this is wasted work. It would be better if we could cancel the losing thread when the winning thread finishes. The threads ability exposes some helper functions like threads.race and threads.read, which help with scoping cancelable work for you. Our new threads program automatically cancels the losing thread when one finishes first, so we don't see the still working messages from the losing thread. In structured concurrency, parent threads should respect the lifetimes of their child threads unless explicitly detached. Let's see what that means in practice. Without threads, This program creates a promise that is never written to and will never complete. But the parent thread does not actually wait for the child thread to finish. With threads, by using threads.scope and threads.fork, parent threads will respect the lifetimes of their child threads. This also has implications for resource management, since a parent thread's finalizers will wait for its child thread's finalizers to run before exiting the scope. Say your program really needs the fire and forget semantics of unstructured concurrency. Instead of using the regular io.fork function, you can still use the threads API. For folks who want fine-grained control over cancellation of child threads, you can use the threads.detach function to create a thread that is not managed by the parent scope. Later, you can manually interrupt it with threads.cancel. Okay, to recap, the threads ability provides a safer and more ergonomic way to write concurrent programs. It introduces structured concurrency and safer resource management through scoped thread lifetimes and finalizers. Many of the functions from the io.concurrent API have a correspondingly named threads version. Give them the shot instead of relying on the low-level concurrent API directly. And if you run into any trouble or want to learn more, head to the Unison Discord, and we would be happy to help.